Thank you. When you see a photo such as this, as hurricane professionals, trained to ready the public for preparedness and keep them safe from harm, what does your intuition tell you here?
How
about this? What does your intuition tell you about a unit that's apparently held down by sticks and CMU blocks?
It doesn't meet code.
It's a lot of work to haul those bricks.
What does your intuition tell you is going to happen when a windstorm occurs here? Would this not cause damage to the building, possibly harm to human life? Perhaps it would cause destruction such as this, or like this. How many millions of dollars throughout the nation, this one's hanging by a thread, improperly designed, how many millions of dollars were lost due to this faulty solar array? And hurricane debris is one issue, and we discussed that. We're all familiar with hurricane debris. If you're in Florida, you've probably photographed it in your backyard, or you might have seen it. If you're not from Florida, you may have seen it on the Weather Channel. But the forgotten issue is air and water infiltration. When a rooftop unit is ripped from the building, the nice 3-foot by 3-foot hole that's now left in the roof allows a tremendous amount of water to pour in. Sometimes 20, 30 inches of rain comes in from a hurricane. So it causes mold, it causes harm to the building itself. And why is this really important? Are we really here to save a few $100s on our air conditioning unit, commercial or residential? We're not here to save a few $100 on an AC unit. And we're definitely not here to bully the air conditioning industry into getting compliant. But what I believe we're here, and of course I try to make everything meaningful in my life, but I think that what we do is we protect the pursuit of happiness. Something that's ingrained in our nation, that we are the silent army of engineers, architects, specifiers, doctorates, that know how to protect the pursuit of happiness for the rest of the citizens. That they can walk around and know that their property is safe and that they will be covered come what may, even in a design event, even in a disaster situation. A little bit about me. I'm a professional engineer and I am the Vice President of Operations at Engineering Express. We are licensed in 23 states and another 10 states, so a total of 33 state licensures. And I'm the co-author of this forthcoming WIN standard by the AHRI, the American Heating and Refrigeration Institute, which is called 1310P, which seeks to solidify a lot of this data for rooftop structures. There's been a, as you've probably seen in a lot of these presentations, we're all learning as we go. And there's new studies that are coming out almost yearly, almost monthly really, regarding rooftop installations and why they're important. And Engineering Express provides designs for some of the companies that you may have even walked into today or yesterday, or your family may walk into at any given time. And by doing these product evaluations on such a repetitive level, it enables us to see the trends in the industry and how that correlates with the research that's being done on the educational side. And a personal favorite of mine was Hurricane Sandy. I was drastically affected. I was a 10-year-old little boy. And I don't know if anyone remembers Hurricane Erin and Hurricane Opal, 1995. Hurricane Erin hit, and then 55 days later, Hurricane Opal, they're both Category 3 storms, hit within 30 miles of each other. So we had no sooner picked up all the pieces from Hurricane Erin, and wham, got hit again by Hurricane Opal. And Hurricane Opal actually triggered the creation of the Florida Building Code. The governor was told, you know, this is a mess. We've got hurricanes hitting, and we need something specific. And so I love hurricanes in my blood, and that's actually a picture of me about a year ago, this time, on one of the structures that had collapsed. And it gave me a really insightful view on what's happening in the field versus what's happening in the office of an engineer or the office of, let's say, a contractor or a builder. So really, what is the big deal? All of this just for exposed equipment. Well, there's a cascading damage profile that occurs. When there is a restraint failure, when the cabinetry fails, there's a series of steps that occur that will cause damage to the property and possibly damage to adjacent properties or even human life. So the first thing that happens is the unit itself falls off of the stand, kerplunk, right into the roof membrane. We have a nice dent there where water will intrude into the structure. And then as the wind starts to pick up this piece of steel on the ground, it tumbles, ka-plunk, 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 all the way down the roof membrane, causing more dings and more notches into the roof membrane. And then if it is successfully lifted from the building, which oftentimes occurs, believe it or not, these units are only 100, 200 pounds, easily lifted at the top of the roof, they become flying debris. And when it impacts the adjacent building, it may either damage the cladding, or worse, it can hit a window, which may not be prepared for impact, depending on its elevation, and depending on the age of the building, and pressurize that building and cause catastrophic damage to the building next door. And if it doesn't hit the building next door, it may fall directly down, it could injure someone that could be staying there. You saw the picture of the car. And lastly, the water that could come in the opening that is now left without any protection to it. And in all cases, there's danger to those occupants. The wind information, the data that we get and that we've seen, it started, actually there's a little, get here, in 1944, and anyone that deals with wind pressures will kind of have a chuckle at this, that the steel building commissions, when they first did their wind tunnel test, they created this chart. This was wind design back in 1944. And one of my favorites here is a fresh breeze, 10 miles per hour, 0.4 pounds per square foot. And here, violent hurricane, 100 miles per hour. And we just heard from Dr. Condon. We're way past 100 miles per hour, and we're well past 40 pounds per square foot. So there was a time when it was much simpler. Nowadays, you can see, starting here in ANSI 58, 1972, these books get thicker and thicker and thicker. And now we have ASC 710. And something I'll bring up at the end of my presentation is a new standard by the AHRI that we are almost complete with, called the Wind Load Design Standard for HVAC equipment, tying all of this information, all of the new studies together. This is the basic force equation. The reason I highlighted this GCF factor in red is because this is where all the stink happens. This is where all the, everyone has a different opinion, the code changes, and it significantly ramped up some of the pressures, which, as you can imagine, caused quite a stir in some project sites. As far as studies, one of the most important things to know is where we get this information. So, a quick background, CERMAC in 2001, if you've never seen these studies, I urge you to read them. They're absolutely fascinating if you're interested in wind design. And in 2001, CERMAC, he had the original study that was adopted into ASC 705 for the lateral multiplier. So that GCF, he realized that there needs to be a 1.9 factor applied to the basic wind pressure. So that was the beginning of the pressures going up for rooftop equipment. Then Tim Reinhold in 2006 had another study where he studied the flow separation and commented that we also have some uplift that we should really be considering. But it wasn't until Trzuk in 2007, he had a study that was actually adopted into today's current ASC 710. And he said, wait a minute, it is 1.9, but there's also a 1.5 times factor for uplift. So he created the idea that there's two separate orthogonal wind loads that are occurring on rooftop equipment. And then Irwin in 2011 at the Florida International University, the Wall of Wind, actually said, well, I hate to tell you folks, but it's not 1.9, it's 3.1. There's a huge difference in what we saw in Florida International University. And then Morrison in 2013, the IB Institute of Business and Home Safety, had the most recent study, which was where they, and I'll cover this, where they debated the effectiveness of ASC 710. Some of the formulas that you would see in ASC 705, which up until a few years ago was predominantly across the entire nation, they would have this lateral multiplier to buildings 60 feet or less, and the little anomaly was that the next door building that was just 61 feet didn't have to use the multiplier. So there was a bit of, as you can imagine, a bit of a fuss about that. When that was upgraded to the national version, they kept the 1.9, they kept the 60 feet, and they also added that study from Trzuk 2007 that there's also an uplift multiplier that occurs. And Florida's always got to be special. Florida says, well, forget all of this, we're going with 3.1, and we'll keep the 1.5 as well, and we're not even doing 60 feet, we're going to do all building heights. And this has tremendously increased the wind loads on rooftop equipment in the state of Florida. So all three of these areas were new and had to be accommodated for by the engineers. Now let's get into the physics of how wind affects a structure. In addition to your basic force coefficient, so your basic wind flow parameters, Wind loads that are on rooftop equipment can be greatly affected by how the wind is flowing over the roof. The problem with wind is that it cannot quite negotiate sharp corners. So what we get is we have this flow separation that occurs. The wind actually separates from the building, which causes all this turbulence on the edges of the building. And then it will actually reattach itself to the building at a certain point downstream and continue the flow. What's fascinating is that these increase in the roof loads also increases the loads on the equipment. Anything that's in its path will be increased. This is a study that was done, that was over-animated, so it's a little bit more colorful than it needs to be, but it was on solar panel arrays and how those are, they're drastically affected by the eddies and turbulence that's caused on the building. So these high suction regions on the rooftop occur very notably in wind tunnel studies, and that's where these studies are coming from. The same thing happens as localized vortices, even on residential structures. So this is a very common effect that's happening. And if the roof is large enough, make sure that plays. If the roof is large enough, the flow features that's created along the edges actually dissipate. The flow that is separated becomes reattached to the building, and what you have is wind flow that's similar to the flow over a flat open area. So we have a tremendous increase in speed as it flows over the building, and at the point that it reattaches, it's almost as if the building itself may as well be a flat open field. And the equipment can be especially affected by this whenever these special wind regions are active in a building. And we talk about the angle of attack of wind. The perfect angle, this is where we get these very, very high multipliers. And this is where more of the studies need to be done to determine if those are true. So when I say lateral force coefficients, this is if you look at it, if you cut an air conditioning stand at a unit in half and look through it, you would see these lateral coefficients from the wind. You would see uplift as well, which has recently been introduced. And the overall effect is to cause this to overturn and pry itself off of this stand or this support. And the IBHS, Institute of Business and Home Safety, created the 2013 study that their objective was to determine if the ASCE wind load provisions are accurate without being too conservative. And what they found was that when they increased the elevation of the equipment above the roof surface, naturally they had higher wind loads. But what was occurring was that the results from the unit experiencing higher wind speeds were happening in this separated shear layer. So we don't yet have wind tunnel tests, even in a massive facility such as this, that can create a building long enough to allow us to study the turbulent edges as well as the reattachment point downstream. So we tend to have to be a little bit conservative because otherwise we have to build a football field of a building to study something that's fairly simple and benign in certain industries. So this is how they set that up, and they determined that there's a certain ratio. When there's a certain ratio between the height of this building and the height of this unit, they noticed that this shear layer, this boundary layer, had different values, and that has not been included or indicated anywhere in the code yet. Another interesting thing, and if you were here at the morning meeting, we discussed some of the screen information. They tested a unit, and it's hard to see here, but they essentially got information on a unit that was hidden behind other units. It was downstream, downwind. And what they found was that there was a substantial reduction in wind loads, almost 70%. Dr. Zizis that was here this morning had a 58%. So there was a decrease in wind loads. Hooray! The problem is the building code doesn't allow anyone to use these reductions. The zoning committees, let's see what we have here. The urban planning and zoning departments in the building departments will say, hey, you need to put a screen up. We don't want to see these ugly units. Put up a 6-foot screen. We want it prettier. So they put up a screen, and no one gets to use the provisions that are found in wind tunnel tests that these screens actually alleviate and reduce the wind pressure behind them. So the engineers are still over-designing because the code has not been, enough research hasn't been done and implemented into the code for that. In fact, ASC actually has language in section 29.1.4 regarding shielding that could be interpreted as prohibiting the use of any reductions at all. And if you read the intent of that, it was actually to prevent engineers from just arbitrarily reducing wind loads based on surrounding terrain. In fact, the code does allow reductions in something very common we call a parapet. They do allow zone reductions behind the parapet because it's recognized that that will effectively shield certain parts of the wind. So the long story short is that IBHS realized that a substantial load reduction can be achieved through these shieldings, and they recommended that more rigorous studies be done. Ingersoll Rand and Carrier don't need to create an air conditioning unit made out of titanium if we can properly allow these screens to do their job and take care of that wind load for us. Another thing that they noticed was that the type of venting style, the porosity of the unit, didn't really affect the lateral wind loads. Because in reality, there's a lot of coils, there's all sorts of obstructions that are still inside the unit, even though there's vents in the left to right lateral direction. But in the vertical direction, the uplift, if you can see some of these maxes and means here, this is ASCE's standard of 1.5, and this is the maximums that are occurring. And you can notice that this is a solid box, got close to the right uplift that's in the code. But the rest of the vented styles actually had a reduction. So the study realized that the model scale wind tunnels, which typically model these units as closed boxes, are overestimating how much uplift is actually occurring. So they not only recommended that the screens be looked into, but that uplift may be a little bit too high for what's really happening in the real world. One question that comes up, or should be asked if you're a wind professional, is if it's any kind of exterior equipment, is it on the ground or is it on the roof? On the ground, you may have 45 pounds per square foot, while on the roof you have 145 pounds per square foot, plus uplift occurring. And that is a substantial change. It's a drastic increase in pressure. And the unit tie-downs are not always engineered, and the unit cabinetry is not always certified. So the industry is starting to slowly move into the correct direction, same as glazing industry has done long ago, which is to make sure that not only will the module stay in place and clip together, but that the internal components are not going to pull itself apart. There's no good having a curtain wall in place. If one piece of glass flies out, the whole thing's got to stay in, anchors and the entire assembly and all. And this industry is slowly starting to understand that that's also needed. And shape is important as well. You can imagine a rectangular unit is going to resist wind a lot more than round would, and ASCE allows reductions or adjustments for round. So a quick example of Florida Building Code 2007 versus 2010. We'll say we're in good old Fort Lauderdale, exposure C on a 5-story building, and a simple 30 by 30 inch cube unit. In the old building code, we would have maybe a 97 pounds per square foot, which, by the way, even before that, it used to be only 50 pounds per square foot, so even this number is higher than what it was years before in 2007. Nowadays, that number is 135 pounds per square foot. So anything on the roof is experiencing and required now to have this extreme wind load applied to it. In fact, 2007 and 2010 Florida code required that the unit, the actual equipment, be certified. But Florida legislative rule disagreed and said, well, tell you what, we're going to say nobody needs to worry about this for now. It's deemed to comply, and we'll worry about this in the next building code cycle. Well, the next Florida building code is the end of this year, and every manufacturer, Trane, Carrier, Ingersoll Rand, and to name a few, are all waiting to see, are we going to get it written out again? Are we going to get exempted? Or are we really going to have to comply with these numbers? And since this is the third time it will be in the code, my firm belief is it won't be exempted again because they've had plenty of time to prepare. So what do we look for? Well, we look for what's the allowable capacity of the product and what's the required demand at the address that it's being installed. We have to make sure that the capacity is greater than the demand. So if we have, let's say, a product certification sheet, and this sheet is certified by the manufacturer, a professional engineer, or a test lab, it's certified for 100 pounds per square foot. Well, over at Smith Construction's job site, they need 47 pounds per square foot on their unit. This is less than the 100. Therefore, the unit will stay in place because the loading is less. This is really no different than when you size an air conditioning unit for your home to make sure your home stays nice and cool. You got to have enough power to keep your home cool. So you have to figure out what's the capacity of the unit and what's the demand that's occurring inside the home because of your sunlight and your windows. So the American Heating and Refrigeration Institute standard, 1310P, will be coming out towards the end of this year and provides a unified national approach so that all manufacturers are designing under the same standard. It can be used by manufacturers to get their own product rating, and then it will create a general ease of permitting so the building officials aren't left with stacks of paper that they've got to sort through. This will hopefully simplify that process. Something that a lot of mechanical code enforcers may be familiar with is this certificate of product ratings, cooling capacity, etc. And they'll just add down at the bottom, Here's our wind rating. And it's very, very important. There's nothing you leave my speech understanding today will be this, is that there is no such thing as a wind rating for a wind speed. There is no, I'm certified for 170 miles per hour. Doesn't exist. Because 170 means another 10 variables to figure out what the number is. So the only thing that can really be certified is the actual pounds per square foot, the actual value of that pressure. And then it's up to code officials and engineers to understand if 170 on the coast is greater than or equal to what is rated at 100 pounds per square foot. How will this all play out? Well, we have engineers, building officials, insurance companies on one hand, towing the line of safety to the public, and we have manufacturers and trade associations on the other hand, understanding that this has to be economically viable. We can't sell titanium diamond-plated air conditioning units. No one's going to buy them or care about them. So there's a balance there that occurs. And my belief is that as we go through time, these codes are becoming stronger as new data is brought to light. There's about 5 items here that I hope will clear up some confusion. Currently, the lateral wind multiplier, it's 1.9, and it's for buildings up to 60 feet. The next ASCE version, it's slated, it'll keep that, but it will be buildings of all heights. They've removed the anomaly. In Florida, currently we have this 3.1 factor. At the end of the year, 3.1 will only apply for Broward and Miami-Dade, and the rest of Florida will comply similar to how ASCE does it for the rest of the nation. For uplift, again, removing the 60-foot limitation and making them for buildings of all heights. And for Florida, no changes expected, same process for uplift. There is a lot of confusion on where the wind pressure is actually applied on the unit, and that is being worked out. It's always at the center of the equipment. Some engineers were using the mean roof height, which actually is in ASCE for certain configurations, but the problem was the unit might be 10 foot tall, and they're missing a huge gap in wind pressure. So it's always the centroid. And lastly, there is no guidance. There's no current guidance for ground-mounted equipment, so AHRI seeks to work around that. There is a wind loads on signs method, but it's a bit conservative. It doesn't allow for all of the factors that really are at play. So AHRI, this standard 1310P, will really solve all of that. The conclusions are that the wind load requirements for rooftop mounted equipment has substantially increased based on new testing, and that inadequately certifying the restraint systems for those units causes property damage and cascading loss. The solid box wind tunnel tests are likely overestimating the uplift forces, and more work needs to be done to study that. The centroid of the unit is where we place the wind load, and the coefficients in 710 are adequate, except that more information needs to be studied in terms of elevating the roof above the surface, as well as coefficients on location. So different coefficients should be applied. Right now, ASCE universally applies those coefficients no matter where on the roof you are. It's believed that with new testing that these coefficients really change based on the ratio of the height of the unit and where the edge is on the roof. And lastly, the substantial wind load decrease that occurs when screens are placed needs to be studied so that engineers and manufacturers can use those reductions and still provide an economical and safe design. A few design resources for you all. FloridaBuilding.org has the Florida Building Code. Engineering Express, dngexp.com, we have free wind load calculators that I'll have a little animation of the next slide. ApprovalZoom.com is where